It started.
Okay. Can you guys see my screen?
Yeah, we can.
Okay. Perfect. So for those of you who find what we're doing to be like, if you know already what we're doing, then you can come back to these buffer problems and try them while we go over that stuff. So you can take a screenshot of this. I'll wait a few seconds and yeah. So, okay, perfect. Hi, everyone. I am Raya Chatterjee, and I am really happy to be speaking today on geometry, which is basically my favorite topic. So, the name of this lecture is basically the foundations of geometric thinking. And I named it so because I thought that the things I'm going to discuss today are basically the basic tools that you need while solving geometry problems. So that's why it's called the foundations of geometric thinking. So we are going to go over some configuration and also some trigonometry stuff that is going to come in handy while we solve the problems. And we are going to have a wonderful collection of problems. I mean, I have some really interesting problems, and the last one is obviously like a total awesome one. I mean, it's one of my favorite geometry problems of all time. So stay tuned till the end. Okay. So basically, the first thing I wanted to say is that I'm going to start off by talking about some configurations. So one of the configurations that is like the most basic and comes up a lot in Olympiad geometry is the 9-point circle. And please forgive me for my really bad handwriting. I'm not used to writing like this, but yeah, it's okay. So before getting to the 9-point circle, what we want to do is we want to prove this orthocenter reflection. So what does orthocenter's reflections tell us? It is basically the fact that the reflection of orthocenter across any of the three sides of a triangle lies on that on the circumcircle of that particular triangle itself. So yeah, so we have a diagram here, and H is the orthocenter of this triangle. So what we want to prove is that the reflection of H across the sides is going to lie on the circumcircle of ABC. So this is totally a basic thing, and the proof is really simple. So I'm just going to go over the proof ones real quick. Okay, so let us name this point X and this one Y. So what we did here is we basically extended AH to meet BC at X and the circumcircle at Y. And we want to prove that HX equals XY. So that would basically imply that the reflection lies on the circumcircle. So we are going to join BY, and angle YBC is going to be equal to angle YAC. Which is in turn equal to 90 degrees minus C, because this one is 90 degrees and this is C, so this is 90 minus C. And again, since BH is also an altitude, we have this is 90, this is C, and therefore this angle is 90 minus C as well. I'm just going to name that HBC. HBX is 90 minus C. And also we have this and this are both equal to 90, both of those angles, and BX is the common arm. So we have triangle BHX is congruent to triangle BXY. I'm just going to write that congruence, or BYX to be more precise. Therefore, HX equals YX. And therefore, the reflection of the orthocenter H across the side BC, oh my gosh, that's horrible. Okay, so the reflection of H across the side BC lies on the circumcircle of ABC. And we can repeat this argument with all the three sides, and we get that the orthocenter reflections of a triangle lie on the circumcircle of that particular triangle. So basically, what was my motivation behind saying this before we prove 9-point circle? So I'm just going to come to that. Before that, I'm going to paste the diagram of 9-point circle, so we have like ease while proving it. So basically, what is the statement of the 9-point circle? 9-point circle states that the feet of altitudes of a triangle from the vertices to the opposite sides, the midpoints of the three sides, and the midpoints of the segments AH, BH, and CH, where H is the orthocenter of the particular triangle, all of these 9 points lie on the same circle, or they are concyclic. So in order to prove this, we can use synthetic geometry. I mean, there are many proofs using like just simple angle chasing and synthetic geometry, but there's a really beautiful proof using homothency. And it's like homothency centered at H with ratio half, or more precisely, ratio 2. Yeah. So, okay. So for that, what we need to prove is that we need to prove that the reflection of the reflection of H across D, the reflection of H across A prime, and all those reflections lie on the circumcircle of ABC. So we can basically bring those points back into the 9-point circle using homothency, and we can say that those 9 points were concyclic. So yeah, that is basically our motivation. And what is the motivation behind taking half as the scale factor? That is the thing. That is because P is the midpoint of AH, Q is the midpoint of BH, and R is the midpoint of CH. So both of these are equal, and these are equal as well. Double, and these are equal. So if I bring back C to R, A to R, then I'm going to have to use scale factor of half while the homothency is centered at H. So that is my motivation behind using half as my scale factor. And the proof of this using homothency is where the orthocenter reflection comes in handy. So we're just going to go over the proof real quick. Okay. So the reflection of H across BC, let us call this X. X lies on the circumcircle of ABC. Similarly, Y and Z also lie on the circumcircle of ABC. So we just proved that, right? Now we want to prove that the reflection of H across A prime also lies on the circumcircle of ABC. So we are just gonna join this. Exactly. Yeah. Okay. Anyway, this is A prime, right? Okay. So we want to prove that we extended HA prime and let it meet the circumcircle at, say, U. Therefore, we want to prove that HA prime equals A prime U. Okay. So for proving this, we want to show that BHCU is a parallelogram. Why is that? Because BA prime equals A prime C, since A prime is the midpoint of BC. And if we have HA prime equals A prime U, which we want to prove, then we have the diagonals bisect each other, which implies HBUC is a parallelogram. So we are also going to join up these two. And okay, perfect. So the basic motivation is to prove that, like, it's just enough to show that HCUX is a parallelogram. So does anybody have the proof of this? Would anybody like to tell me? Anyone?
Angle BHC is 180 minus A.
Okay, BHC is 180 minus A. Okay,
And angle
yes.
BUC is 180 minus A.
Yeah, perfect.
And then I think we can complete the angles using 1 second.
Mhm. Tell me once you have the proof. Oh, wait.
Uh, uh, are you listening me? Am I audible?
Yes, you are audible. Go on.
Maybe we can use a phantom point u prime on the circle and
Okay.
show that the angle that it makes with the other two vertices is also 180 minus a. Therefore,
Uh-huh.
it should coincide with u and something like that.
Okay. That sounds interesting.
Wait, so we
Okay.
assume U to be like the antipode of A, right?
Yes, I mean, it will eventually turn out to be the antipode of A, but we don't assume it to be.
So what are we like given?
We are given that we extend H A prime, but A prime is the midpoint of BC. So we extend that and it meets the circumcircle at U. So
Okay.
what we want to prove is that H A prime equals A prime U. So that is what we want to show.
Okay.
And we reduced it to proving that HCUX is a parallelogram, but we are not done. Okay, I can suggest something. We can just take the opposite thing. Like we can assume that this and this is equal. Like the proof, like if we want to show that HCUX is a parallelogram, that is also a perfectly valid method. But there is one more way to approach this. We can assume both of them to be equal, and then we can show that um, AU is like the diameter. Like um, someone said the antipode of A, U will be the antipode of A. So that is basically what we can go back to showing. So it would be a bit more convenient. So yeah, let's do that. So since we have A prime is the midpoint of BC, then we have BA prime equals A prime C. And this are also equal. Like we are given that. We are just going the opposite direction. So we have HBUC as a parallelogram, right? Is that all right with everyone? Is everyone in agreement?
Yes.
Okay. So this angle equals this angle. And this angle is again 90 minus b. So this is 90 minus b. Yeah, so I'll just write that down. So angle UBC is 90 minus b equals angle HCB. All right. And now angle ABU also equals B plus 90 minus B. Can you see why? This is B and this is 90 minus B. So this total angle is B plus 90 minus B, which is just 90 degrees. Therefore, since AU subtends a right angle on the circle, we have proved that AU is the diameter of the circle. So, okay, so is that clear? I mean, does anybody have any doubts on this?
No.
Okay, perfect.
1 second. Didn't we
Uh-huh.
assume that HA is equal to AU?
Yes.
So don't you have to first prove that U lies on the circle?
I mean, when we proved that this angle is 90 degrees, that means it lies on the circle, right? It's just a semicircular angle. If it doesn't lie on the circle, it can't be 90.
I mean, it could just lie on that leg of the 90 degrees, like somewhere.
Uh,
Sorry.
okay.
Hello.
Yeah, hi.
His claim is correct that we have to first show that U lies on the same circle, but we can easily show that we have already ABU is in a same circle and also ACU in a same circle. So all these 4 points is in a same circle. So by that claim, we can say
Yeah.
that U lies on the same circle.
Okay, yeah,
Yeah,
we can complete it that way.
right. Okay. Perfect. So yes, so we have shown that, like, is everybody clear with this reflection over the midpoint of sides? Any more doubts? I'll take that as a no. Okay. So the reflection of H across the midpoint of BC, CA, and AB also lies on the circumcircle, right? So like we can take homothety centered at H with scale factor half now. So what do we have? Like, let us name these points. So this is U, and the reflection over the midpoint of AC is V, and this one is W. Okay. So what we have right now is that A, B, C at the points, yes, X, Y, Z, U, V, W, all concyclic. Is that right? Okay. And therefore, we can take a homothety with scale factor half. So U goes to A prime, X goes to D, B goes to Q, Z goes to F, W goes to C prime, A goes to P, Y goes to E, and V goes to V prime. Therefore, since homothety preserves cyclicity, I mean, we had a homothety lecture a couple of days ago, couple weeks ago, I guess. So I will not go over homothety again. So since homothety preserves cyclicity, we can say that all these points, all these 9 points lie on the same circle. So that is basically the proof of the 9-point circle. Any doubts, anyone on this? Please feel free to speak up. I mean, a yes or no would be appreciated.
Wait, for the like
Uh-huh.
reflection across the midpoint, is
Yes.
there a way to prove it by just like intersection of the HA and the circle?
HA. HA and the circle intersects at X.
I mean,
H.
like, no, the H and the midpoint. A dash, for
Oh,
example, A dash, yeah. I couldn't see
okay.
that. So is there a way to prove it that way? I was wondering. H and A dash, not A.
Ah, sorry.
Because that was like the first way we discussed. So I was just curious if there was a.
Okay, perfect. Yes. So H and A dashed. Okay, so this meets at U and these are equal. So I just want to prove that this and this are equal. So what I'm going to do is I'm going to prove that this is a parallelogram. Oh my gosh. It looked like a line segment. All. Okay. So I am not exactly sure right now, but I am pretty sure that we can prove alternate angles to be equal here, and that might help our cause. I'm not exactly sure. Okay, I think I have it. Give me a second. I'll just think. Okay, so think 90 minus A, 90 minus C, C. This is B. I haven't really thought about it that way, but yes, 90 minus B. And uh-huh. Okay, so I don't think there's a way to prove this with like this argument because like yeah, okay, so we don't know the exact location of C and the relation like of U and the relation of U with A right now, right? So we can't find out the angle UBC, and if we found that out to be equal to 90 minus B, we would be done because alternate angles, and therefore these two would be parallel, and by a symmetric argument we could also show that this and this could be parallel. So I don't think this could be done, but I will try to uh, think about this and let you
Yeah,
know.
sure.
Excuse me.
Thanks.
Hello.
Yeah. Do you have a proof? That would be helpful.
I'm not sure, but
Yeah,
we have
please go
angle
on.
BHC equals to 180 minus A,
Okay.
and similarly BUC is also 180 minus A. And one of the diagonal is bisected. So is it
Yes.
enough to claim that it is a parallelogram? Because the opposite angles are equal,
Yes.
and one of the pair of opposite angle is equal, and one of the
Yes.
diagonal is bisected.
Uh-huh.
So can we claim it from here?
No, because we don't have a congruence here, right? How can we claim this? I'm not sure. I don't think that works.
We can come back to this later, I think.
Yeah,
True.
sure.
True. Okay. Thanks for that. And okay. So this was one configuration I was curious to talk about. And let's go on to the next one then. So for the third one, we have the three tangents lemma. Okay, let me tell you this. If you have done EGMO, then all these will seem extremely familiar to you, but then please try the buffer problems that I gave at the start. Okay, so the three tangents lemma, if I state this, it will appear to be a really random thing because it doesn't have as much significance as our common theorems and lemmas in geometry. And when I first read it, I was totally skeptical that how can we use this as a lemma? I mean, it was listed on EGMO as a lemma. So I was totally skeptical that I can't use this as a lemma. This could be treated as a problem, but not as a lemma. That was until I saw an RMO problem that used the three tangent lemma. So, okay, so my motivation behind going over this lemma is basically to do that RMO problem and like discuss it. So, yeah, I mean, it doesn't appear to be as arbitrary as it seems. So, that was the point I wanted to make. Okay, yeah. I'm just going to state the three tangents lemma right now. Yeah. So, what is this configuration? We have a triangle ABC, and H is the orthocenter of the triangle. And now BH and CH are perpendiculars, like altitudes from B and C to the opposite sides. Therefore, we basically know that AFHE is a cyclic quadrilateral because the opposite angles are supplementary, and M is the midpoint of BC. So what this lemma claims is that ME, MF, and the line through A parallel to BC. All these three lines are tangent to the circumcircle of AFHE. I'm just going to write that down. MEMF, and this, let's call this line L, and L is parallel to BC. So MEMF and L are all tangent, okay, to circumcircle of AFHE. So this is a statement of the three tangents lemma. Is this clear? Okay, I'll take that as a yes. So the proof is very simple. Should I go over the proof, or do you guys need some time to think about it? Or should I just say it?
Can I have a look at the buffer problems once? Because I joined a bit late.
Okay, yeah, that's fine. One second. Yeah, these are. Like, take a screenshot or something, I guess.
Thanks. I'm done.
Okay, so back to this. Should I do the proof, or do you guys need time? Please, like, do a quick vote, like yes or no. Okay, I'll go over the proof. Okay. So basically we have AFHE is a cyclic quadrilateral, and also by some of the like most elementary theorems in geometry, like we also have BFEC is a cyclic quadrilateral. This is because angle BFC equals angle BEC, which is 90 degrees. Both of them are 90 degrees. And since BEC and BFC are 90 degrees, we can also say that BC is the diameter of the circle. And since M is a midpoint of BC, then M is basically the center. So we are going to need this information. But before that, the first thing I'm going to do is I'm going to prove that L is tangent to this circle. So for that, I want to establish a similarity. I'm claiming that triangle AEF is similar to triangle ABC. And this is not hard to see because BFEC is cyclic. Therefore, by exterior angle theorem, this angle is angle B. And different color, this angle is angle C. Okay, so yeah. So like due to AAA, this holds. And since this holds, again, like L was parallel to BC, right? Therefore, this angle, the angle between L and AE, is going to be equal to this angle, like alternate angle theorem. So this is just C. This is also going to be C. Okay. So since we have the angle between L and AE, like this one, this angle equals this angle. So I can use something like the converse of alternate segment theorem. So by the converse of alternate segment theorem, I basically have that L is tangent to, let's call that omega. Yeah. So, okay, we have proved the first part. Is this clear? Does anybody have any doubt about this? Okay, I'll take that as a yes. I mean, it would be really encouraged to speak up. Okay. So, yeah, AEHF is a cyclic quadrilateral, and therefore, our next aim would be to show that ME is tangent. We are going to use the same argument, the alternate segment theorem thing. And okay, so for that, we are going to chase some angles. So what is this angle? What is this angle? This angle is basically 90 minus C, right? And M is the center of the circle that consists of these 4 points. This, this, this. Therefore, MB equals MC equals ME equals MF because all 4 of them are equal to the radius of that particular circle, right? Okay, so since MB equals ME, I can say that this angle is 90 minus C as well. And notice that H is the orthocenter, so I can just produce AH to meet BC at D. This is going to be 90, and this blue angle out here is going to be equal to 90 minus C. Therefore, again, by alternate segment theorem, by the converse of alternate segment theorem to be precise, I can say that ME is tangent to the circumcircle of AEF. Again, by the same argument, ME is tangent. And by an exactly symmetric argument, I can just say that MF is tangent. Okay. So is this question clear? I mean, is this proof clear? Does anybody have any doubts about this?
I'm like doing the buffer props, so I might not be like responding so much.
Okay. I mean, other people speak up, please.
Yes, it's clear.
Okay, perfect. Thanks. Okay, so let's do our first problem. And okay, there's an unwritten rule that I'm going to employ to this session, which is that I'm not going to reveal the sources of problems until I entirely solve them. So yeah, so actually I revealed this problem that it's from a previous RML, but from the next problem onwards, I'm not going to reveal the source. So here goes the problem. Yeah, you guys can try this. Zoom in. I am going to give you guys like 3 minutes, 3 to 5 minutes to think about this. Please tell me if you have any ideas or any questions. Okay, so you guys can still see my screen, right?
Yes.
Perfect.
Just want to confirm, but is L, M, and N collinear?
Yes, it is eventually going to be. All right. So, okay, guys, keep doing the problem. I'm just gonna copy paste the diagram that I drew from GeoGebra. I mean, my hand-drawn diagrams are too pathetic. Yeah, yeah. Okay. So, okay. Do you need a bit of more time to solve this, or should I start with some hints?
I think you can start with the hints,
Okay.
but
So yeah.
like
Go on.
2 minutes a bit more.
Okay, perfect. I mean, yeah. Okay. So let me give you some ideas on what we can try to show in order to proceed with the problem. So the first thing we can try to do is we can show that LM is somehow perpendicular to FE. Like these are the hints, right? LM is perpendicular to FE. And I'm also going to have NM or like more like LN is perpendicular to FE. That's what I'm going to have. And from these two, I will eventually be able to conclude that L, M, N are collinear. So that is my aim. That is the first hint, basically.
Maybe we could take that L is, well, L is equidistant to E and F since it's the center of the circle with diameter AH and both of them lie on diagonal.
Yes. It is going to be equidistant from E and F. Yes. And
M is the
how do you?
midpoint of chord EF. So
Exactly. Okay. Congrats. You got the first thing. So LM is perpendicular to EF.
and for the
Yes.
second part, I guess 3 tangents should work.
Exactly. Okay. So that is where the 3 tangent comes in. So, okay. So like by 3 tangents, we have EN and FN. EN and FN are tangents at E and F. So this part is important, right? At E and F. Because if we have a circle and we have 2 tangents that intersect at like X, and if we join the chord of the tangent touch points and we take the center, then if we join the point of intersection of the tangents and the center, we will get that the chord is going to be perpendicular to it. And more importantly, I mean, more precisely, it's not going to be useful in this problem, but these 2 segments are also going to be of equal length. So we can just prove that from a simple, congruence. I mean, these 2 triangles are just going to be congruence. Like, do you see that? Why that happens? Like,
Yes.
Yeah, due to
okay.
congruent triangles.
Yeah. Okay, perfect. So they're going to be perpendicular. So from this one, I can say that NM is also perpendicular. I mean, not NM precisely here, NL. L is the center. I'm just going to write this down. L is the center of AFHE. Yeah, so NL is perpendicular to FE. And since LM is also perpendicular to FE, we have like this part. We have LM and N are collinear. Is that clear? Anybody has any doubts till this?
No.
Okay, perfect. Yeah, so my next target is going to be, I'm just going to claim this. It is FMNY is cyclic. Do you see why?
Wait, so we can just angle chairs after this, right?
Exactly. That's the whole point.
Wow.
Okay, so FMNY is cyclic because like NM was perpendicular to FE, and this one is also perpendicular by construction. So just opposite angles are supplementary. So this claim is proved. So since this is cyclic, I want to show that angle XYM, like what do I have to prove first of all? That is very important. I have to prove that XM is perpendicular to MY. So if I show that angle MYX plus angle YXM is 90 degrees, then I'm done basically. So I want to show that angle MYX is going to be equal to 90 minus A. So that is my claim. And how does that happen? So MYX.
Yeah, I think I'm done.
Okay, perfect. Do you want to say the solution?
I mean, I think there are other people trying, so it wouldn't be
Should
fair.
I finish it? What? Okay. I mean, I was just going to. But anyway, can you guys please tell me if you need some more time to try this? Right. Actually, one more thing. Just my OneNote screen is visible, right? Nothing else.
Yeah, only the one.
Okay. Thanks. Other people, please speak up. Okay, I'm just gonna solve the problem. So yeah. So angle MYX is going to be equal to like yeah, okay. So MYX. Okay, yeah. I actually want to give you guys a little more time, but fine. Okay. So angle XYM equals, where's the angle XYM?
Should it be equal to F and M?
Yes.
Because the complementary angles plus
Yeah.
the angles which are in the cyclic quadrilateral, they were
Yes.
the
Perfect.
congruent angles.
Yes. Perfect. So XYM is equal to FNM, and which is in turn equal to 90 minus MFN. I'm just gonna write that down. 90 minus what was the name? MF this one, NFM. 90 minus NFM. Perfect. So now we just need to compute the angle NFM. So what we want to do for this is that this angle, like this one here, is 90 minus B, because CF is the altitude and N is the midpoint of BC. Therefore, N is the center of the circle BCEF. Therefore, BC equals BF. Therefore, this angle right here, this blue one, is also going to be equal to 90 minus B. Is that clear, everyone?
Yeah, but if F, M, and Y, if it's cyclic already, we know it, then is
Yes.
it just a property of cyclic quadrilaterals?
Okay, which angles are you trying to say? Can you go once again?
Angles angles F, Y, M,
Yes.
and F and M.
FYM. Yes, FYN and FNM are equal. Yes. That's what we have done here. But that is not what we want to show, right? What we want to show is that XMY is 90 degrees.
Okay, I see what you mean. Yeah.
I don't think we
Uh-huh.
even need that angle like BCF. We don't need a 90 minus B. Since we know
Okay.
N is the center and E
Yes.
is the chord,
Yes.
so angle FNE is like twice angle FCE.
Okay.
Uh-huh.
So that is like what? 180 minus 2A? Yeah, 180 minus 2A. But MN is just the angle bisector of angle FNE. So it becomes 90
Yes.
minus A if I have
Okay.
one
That's a clever way to do it. Okay. Perfect. So did everybody else understand this? Like we're just done then, right? We just don't have to show anything
Yeah,
else.
it's
We're just
up.
done that
It's
XM.
over right now.
Yeah, it's over. Uh-huh. Oh my gosh. Okay. Perfect. So we did the problem. Yay. Uh-huh. So we're just gonna proceed to the next thing in the list. So that is, we are going to go over trig. A little bit of trig revision and then some really cool problems. And trust me, the last trig problem is going to blow your mind. So yeah. Okay. So does everybody here know like sine rule and cosine rule? I'll take that you're familiar with sine rule and cosine rule.
Yeah, I guess so.
Yes. Okay. Perfect. And okay, so sine rule and cosine rule are like the two commonest trig stuff. So I'm not going to go over it again. And I'm going to go over some angle identities like double angle, half angle, addition formula. I'm just going to do a quick recap of those and I'm going to proceed to the problems. So the first thing that I wanted to say is that Like we should revise the addition formula. Yeah. Okay. Perfect. I think many of you are familiar with these, so please feel free to go back to solving the buffer problems. Yep. So okay. Sine A plus B is sine A cos B plus cos A sine B. And the signs just reverse. Yeah. Cos A plus B is cos A cos B minus sine A sine B. And this is plus, this is minus. Tan A plus B is tan A plus tan B over, oh my gosh, terrible straight line. 1 minus tan A tan B. Okay, so yes, these are the addition formulae, and next comes the multiple angles. So just sine 2 theta and sine 3 theta, that sort of stuff. So while like talking about multiple angles, there's one thing I want to tell you that like I hate memorizing multiple angle identities and I tend to forget them. So just like find them out using the addition formula whenever you need them. So like sine 2x is 2 sine x cos x, and sine 3x is 3 sine x minus, oh my, minus 4 sine cube x, cos 2x is cos squared x minus sine squared x. Cos 3x is 4 cos cube x minus 3 cos x. Tan 2x is 2 tan x over 1 minus tan squared x. So that is basically what like the multiple angle identities are. And okay, so I'm gonna take like your opinion here. So do I need to go over the sum to product and product to sum identities, or is everybody familiar with these? I need everyone's opinion, please. So please speak up. Otherwise, I'm gonna go over them.
I don't think so.
This is really
I think everybody's fine.
okay.
Actually,
Okay.
one guy in chat doesn't know. He said no in chat.
Oh, okay. Perfect. So I'm going to
No,
go
sir.
over them real quick. Sum to prod. Like there are just 4 formulas. So
Yeah, sure.
uh-huh.
What? Yeah, sure, sir.
Oh, okay. The guy in chat knows it. So yeah, sure, that's okay. So okay, I'm not gonna go over them. Oh, Bhairav, you don't know it? Okay. So I'm just gonna go over them real quick. It's not gonna take much time, trust me. Yeah. So sum to product, the formulae are sine x plus sine y is 2 sine x plus y by 2. Ah, what did I write? Okay, I'm so sorry. X y by 2 cos x minus y by 2. And yeah, the first one. Second one is sine x minus sine y. Feel free to take notes and just tell me to pause whenever you want to see something that I've written earlier. Yeah. So yeah, third one, cos x plus cos y is 2 cos x plus y by 2 cos x minus y by 2, 4. Cos x minus cos y is minus 2 sine x plus y by 2 sine x minus y by 2. So these 4 are the sum to product formulae, and these are used very commonly while solving trig and doing trig bash. So I think you guys probably have heard of this. So you can just take a quick screenshot, or if you have done, I can move on to product to sum. But is that okay? Can I move on to the next one?
Yeah, that's all right.
Product to sum. So the product to sum identities come directly from the sum to product. you just need to be able to do the perfect substitutions in order to get them. So they're not that hard to see why we get the product of the sum. I mean, we just add the sum to products and then divide by 2, and then we get the product of sum ones. So I'm just going to write them. I mean, there are only 3 here, so not a major issue. Cos A plus B. Second one, cos A cos B is half cos A plus B plus cos A minus B. Sin A cos B is half sin A plus B plus sin A minus B. Okay, my tablet is not working. What is going on? Yeah, sorry about that. Okay, so these are the 3 important product to sum like things. So these are the only things we need to know, basically. Is that okay with everyone? Can we move on? Okay, I see the chat. Okay, perfect. Let's move on. So I'm going to give you guys a problem that is basically a trig bash problem. And it's not that easy, and I'm not going to reveal the source like I said last time. Let's first solve the problem and then worry about the source. Okay, perfect. So I'm just gonna give you guys like 5 minutes to think about this, and then I'm gonna start with the hints. Sounds good?
Uh-huh.
Mhm. Okay, you guys don't worry about me solving the problem. I just drew the diagram in GeoGebra and I'm gonna paste it and like write some stuff down. You guys need hints or more time to try?
Could you slightly scroll up right to complete the problem statement? It's yeah, there.
Okay, guys, tell me about your progress. Any significant progress?
So we can angle series to get the angles of RQL and RPK, sorry. Yeah.
Yes. Oh my gosh,
So
smart person. Okay, perfect. Uh-huh. These two. Okay, so what do you plan on doing next? Right. I
if you
mean, you
get
got
those
it.
two, I think RQL is 90 plus CY2
Yes.
and RP, what's it? RPK, yeah, it's the same.
Uh-huh.
So if we like
Yes.
can prove like the areas are same, that means by I think there's that RQ into sine of that angle into QL
Yeah.
into RP into sine angle and PK, and the angles are same, so we just need to prove the product.
Okay, perfect. Yeah. But in order to prove the product, you need to actually find out these lengths, right? I mean, finding them out can be quite challenging. Like, it took me a lot of time when I first did it. Yeah. But anyway, your intuition is totally correct, and congrats. So basically, what he said was that we need to compute two angles, and then we need to apply the formula that the area of a triangle is half times, oh my gosh, half times AB times sine C. So this is what we should be focusing on, and this will eventually lead to solution. Yeah.
Yeah,
I'll
finding
give
the
you.
product of the lengths is a bit challenging.
Yeah, exactly. That's the whole point. I know. I
RQ and
mean,
RP seem to be the problem, I guess.
RQ and R. Exactly.
Yeah.
Yes. Okay. So, like, try that for a while. I'll give you a hint to totally simplify that. There's a trick, but try to see if you can figure it out. Should I suggest something? It's going to simplify you.
Just curious, the suggestion, is it like synthetic or is it like trigonometric?
Totally synthetic.
Okay,
Totally
okay, then give a minute. I don't
Okay.
like, I'm like a bit bad at synthetic, so I need,
I mean, it's not exactly synthetic. I'm going to suggest 2 points in this configuration, and after that, it's going to boil down to trig. But there are 2 points on this configuration which are not evident right now. So that would be my suggestion.
okay, is the circumcenter one of them?
No.
No, right?
Think harder. Like what lies on circumcircle of ABC? What point? What interesting point?
R is the midpoint of AC, but AB or AC? That's right. Okay, R is the midpoint of arc AB.
Okay, R is the midpoint of. Yeah, exactly. It is. Uh-huh.
I mean, and then I don't get anything much.
Okay. Yes. Okay, so that is taking you sort of to the right direction. Think harder. I'll just give you like 2 minutes and I'll solve the problem. I mean, if I solve the problem, it takes the fun out of it. Just like. Okay, well, let me make a suggestion then. Think about the points I and IC. I take it everybody is familiar with the in-center excenter lemma, right?
Yeah. So, okay.
You get my point?
Yeah, yeah. IC is the the X center, right?
Yes. Everybody, are you guys familiar with the in-center excenter lemma? Run it, that's fine.
Yeah.
Perfect. Okay. I mean, more people aren't speaking up, so I'm just gonna assume that people are. Yeah. Oh, I see the chat. Okay, nice. So, okay. So the in-center-excenter lemma tells us that like the point I is going to be here somewhere. I'm not concerned about the location of I. I'm just going to use I to help me compute my lengths. Okay. So, and the excenter, oh my gosh, center is somewhere over here. Some over here. This is IC. And the in-center-excenter lemma states that like I, A, B, and IC are 4 concyclic points. And also the midpoint of IIA lies on the circumcircle of ABC. So now you know a nice property about R, that R is the midpoint of IIC. So like, and last hint after that, like if I say more after that, it's basically like solving the problem myself. This is like CI. You know the length CI, right? CI, to compute CI, you can like CI is a known length. Using trig, you can find out CI. And also you can find out CIC using trig, because if you extend these sides beyond, then the excenter, like the X circle, is going to pass like somehow like this. Oh, it's going to intersect. I'm sorry, my bad. My gosh, this is why I prefer GeoGebra. Anyway, X circle is going to look somewhat like this. This is going to be the point, and this one is going to be 90 degrees. I'm just going to zoom out. Yeah, this is 90 degrees, and this total length is S. So see if you can figure out everything in terms of A, B, C, S. Yeah, these 4, and sine, cosine, tangent of all the angles. So that is going to be my hint, that CI and CIC are very well known lengths. So you can just use them to do whatever, like
So
bashing you
RA
want.
is going to be equal to RI.
RA. Okay, 1 second. I lost it. RA. Yeah, all right. Yes, exactly. But finding out RA using Ptolemy is going to take a lot of time. So what I suggest you do is that just find out CIC first using trig, because this triangle, I'm just gonna highlight it. This triangle, can you see it? This big one doesn't look like a triangle, but this big one. Could you see the triangle I highlighted?
Isn't
Yeah.
RA actually easier?
RA.
Yeah, because like
Okay.
using Ptolemy itself. Oh wait,
Ptolemy
yeah,
is
Yeah, I
equal
mean,
to
okay, perfect. You can like go about it.
you'll have to
Yes.
bash.
But
Yeah, no, it'll be too long.
okay, I mean, you
exactly.
can
So
bash. Uh-huh. Go on, please.
yeah, my point was such.
Okay. So, but if you use Ptolemy, there's going to be a drawback that you don't know RB and RA, but they are both equal to each other. And you also don't know CR. So which one are you going to figure out? Yeah. So my entire point right now is to calculate CR. Okay. I mean, calculating CR basically solves the problem. Come on, guys.
Okay, we can
Tell
just
me.
use S
Ah.
minus A and stuff. That's
Yes.
the hint.
You got my point. Yes.
S and S minus A.
S minus A.
Uh-huh.
Still, it's wrong. Isn't there a nicer synthetic or something?
No, I don't think so. This is a total bash problem. I hated it when I first saw it. I mean, I stayed up the whole night trying to find a synthetic solution, and the next day I was asking someone for hints, and he was like, "Why are you trying synthetic? It's just bash. It doesn't have a synthetic way." And oh my gosh, that was a bummer. Oh, anyway, come on, guys. You have any ideas? Um, Okay, 3 more minutes.
Just a thought. Maybe if we could take I's
Yeah.
reflection over the perpendicular line, the perpendicular bisector of
Of
IIC, the perpendicular
okay.
bisector. If we kind of take the reflection of it, then kind of
Uh,
finding CI would be maybe trying to find like ICI.
okay. Basically the reflection of I over the perpendicular bisector of IIC is IC itself, right?
Right, I mean C. So like kind of moving everything from the triangle to its X center. It was just a thought.
Okay. Oh, okay. Well, that is a wonderful method. Like that is totally like called shifting the perspective. I mean, this is not a oh my God, I'm spelling it wrong. Perspective. And this is not a name that I made up. It is named so like you start with a triangle and you convert everything in terms of a different triangle. So yeah, that is a really good way to go about it. But I'm gonna do something that is much simpler, and I don't know why you guys are taking so much time. So should I go about the proof?
I think
Or
IIC is
IIC? Yes.
wait, it's something like one of the two side lengths upon sec c/2. I got
Okay.
confused because my points are like differently named against the question.
Okay. Oh, wow. Okay. I see. Okay. Yeah. One of the side lengths over cos of half of an angle. You are right.
So I have to like really rename the points now.
Wait, what
Uh,
sec coming in?
I mean, just like a side length over like cos of something. So he just said it side length times sec of that. Am I right?
Okay, yeah. Okay, side length over
Yeah, that's what
cos.
I meant.
Yeah. Perfect. Um, how did you figure that out? I'm curious without solving it on pen and paper.
I remember doing it somewhere before. No, wait. Yeah, you can just like do it in your head. Yeah, it's just S minus A. My triangles, what's the name differently? So I can't really explain.
Okay, perfect. That's not a problem.
Oh, wait, yeah. You take S and S minus A. So if you subtract them, because it's like the
Uh-huh.
same angle cos. So you subtract them, you'll get the side.
Uh-huh. Exactly. Yeah. You said that entirely correct, but yeah, we're just gonna go over this, okay, guys, because we have one last problem that I really want to go over. I don't want to go over time. So should I do the solution? It's just bash, it's not nothing special. Should
Yeah,
I
you
do it?
can, yeah, you can
Yeah,
do it.
yeah.
Okay. Okay, perfect. So basically the first thing that we want to calculate is we want to calculate CI. And I don't know why this seems so hard for you. Or I should have said this before, but like if you drop the perpendicular from I to this thing, this angle is C/2. This is R. Therefore, CI is just equal to S minus C over cos C/2, right? Right.
Oh, yeah, it's
Or
C. Okay, right. My triangle was like named.
oh my gosh, 1 second. I wrote that wrong. What?
Right, multiplying it by sec, same thing.
Yeah, exactly. So like I'm not going to go into the deep like calculations, but Ci is going to be equal to S minus C over cos C/2. Do you see why? Because like this is the right triangle and like you can involve stuff, right? And
Yeah, it
there's going to
makes
be an
sense.
R here somewhere. Yeah. Okay. And like okay, C that was like yes. Uh-huh. And similarly,
I don't think
CIC
there's
is
an R. Why is there an R?
I'm sorry, I was just no R, right? You are. Yeah. Okay. Perfect. And similarly, like I can compute the same thing for CIC, right? Because I just highlighted at the beginning that this is a right triangle. So like using that same logic, I can just say that CIC is S over cos C by 2. Make sense? Because this is X. This is S. You guys know this, right? I mean, the length of the tangent from one of the vertices to the opposite X circle is the semiperimeter.
Yeah.
Okay, so perfect. Yeah, so I got CI and
Where does that
CIC.
come from? And just again, is that a particular theorem or lemma?
Yes, it is the extension of the like incenter-extender lemma, you can call it. It's like, it's the extender theorem. I'll just share the, like, I have some notes on that.
I
I'll
mean,
just
the
share them
proof
after
is
class. You
small,
can.
but yeah.
Yeah, it's small, I know. Yeah, this and this are equal. Like, I can like go over it, but yeah, that's fine. I mean,
Yeah,
I'll just
I can
send
keep
you.
later.
Uh-huh.
And nothing.
Okay, perfect then. I'll just not go over the proof, but
You can
this
discuss
turns
it
out to,
outside the class time, I guess.
yes, okay, perfect. That's a great idea. For those who wants to say stay over time, you guys can stay. Yeah. So yeah. So this and this are both equal to S, and since this is equal to S, actually I can't wait to get over with this problem. So I hate bash. I shouldn't say this, but I hate. Anyway. So yeah, this is S, and from that we can say that CIC is S over cos C by 2. And like we can subtract CI from CIC to get IIC is S minus C over cos C by 2. See, that's a nice expression. And like after a bit of trig bashing, I can also say that IR is going to be C over 2 cos C by 2. Because IR,
C cos C by 2 only. There's no S minus C.
yeah, uh-huh.
IIC is just C upon
C.
cos C by
Oh,
2.
right.
It's not S
Uh-huh.
minus C,
I
just
just didn't subtract it, I guess. Thank you so much. And I'm sorry for that. Okay. So yes, IR is C over 2 cos C by 2 because IR is half of IIC. And again, I can say that CR is CI plus IR. Do you guys see why? See, it's just simple. CR, sorry. CR is CI plus IR. Therefore, I can compute CR then to be equal to A plus B over 2 cos C by. Makes sense? I mean, I just manipulated the S and C, and like I substituted S to be A plus B plus C by 2 and like got the 2 to the denominator. Make sense?
Yeah.
Okay, perfect. So like we got CR, right? So that is good progress. And now similarly, we can also get QR to be equal to A over 2 cos C by 2. Like just find right triangles and you'll be done. So LQ can be B tan C by 2 over 2 as well. Like I should go over this. I don't know, I'm rushing anyway. Yeah. So okay, QR is A by 2 cos C by 2, and that is evident because QR equals CR minus CQ. And we know the length CR and CQ, right? Is that clear? Sounds good? Oh, I was just using one.
yeah.
Okay, perfect. So yeah, we have computed CR. And like similarly, I can compute QR because QR is CR minus CQ. So QR, like, okay, we just did QR, right? And again, in triangle CLQ, just look at triangle CLQ. I'll just highlight it. CLQ. This is the right triangle, right? So in this triangle, we can like do the tan C by 2 thing to get LQ equals this. Like this is like from tan C by from tan C by 2 of triangle CLQ. Is that clear?
Yeah, and then we
Yeah,
can just
yeah.
subtract lengths.
Exactly. Next, we want to find the lengths PR and PK. I think all of you have seen the point of what I'm trying to do by now. So in triangle, I forgot the name. The CPK, I guess. Yeah, CPK, yes. Triangle CPK. I can see that PR is going to be equal to B by 2 cos C by 2. After subtracting like lengths, like I knew that PR is going to be equal to CR minus CP, which gives me this. PR is B by 2 cos C by 2. And yeah, similarly, I can find out some related lengths like PK is A tan C by 2 over 2. So we have all the four lengths right now, and like someone pointed out at the beginning, that these two angles are going to be equal. This angle and this angle are equal. So at this point, our aim is to show that LQ times QR equals KP times PR. So yeah, enough to show LQ times QR equals LP times PR, right? So yeah, or yeah, I mean, okay. So like, I'll use a different ink. LQ times QR is basically half of, let me see the value, half of B tan C by 2. And what is QR? A by 2 cos C by 2. Yeah, I'll just multiply both of them. I'll get half of B tan C by 2 by 2 times A by 2 cos C by 2, which equals 1 by 8 AB tan C by 2 by cos C by 2. Agreed? Everyone?
Yeah.
Makes sense? Yeah,
Mhm.
okay. So LP times PR. What was the length? Should have written it down. PR is just B by 2 cos. So like LP is A tan C by 2 by 2. So LP times PR is right now it's A tan C by 2 by 2 times B by 2 cos C by 2, 1 by 8 AB tan C by 2 over cos C by 2. So like we have the same value. So highlight this one. Oh my gosh. Look. Okay. This one and this one. So we have the same value. And since the included angle for both of the triangles is equal, then by the formula that area equals half AB sine C, we have the area of triangle LRQ equals area of triangle KPR. Agreed? Is the proof clear? Everyone? Hi,
Yeah,
please.
it's just
Yeah.
triangle PRQ, but yeah, it works. Like in the last relation.
Go again.
You're supposed to write like triangle LRQ area is equal to triangle KRQ. You made an error while writing.
KRQ. Did I write that? Oh, right. Sorry. I'm so sorry. Thank you so much. And now coming to the source of the problem, I promised to reveal this. So this is IMO 2007 Okay, so people, we solved an IMO problem. And yay. So do you guys want to do one last problem? Or
Fine.
like, okay. And trust me, this problem is super interesting, super entertaining. Okay. There's nothing like about a diagram to draw. Like I'm gonna give you 5 minutes to think about it, and I'm just gonna say the solution after that. So yeah, take your time. Any ideas, people?
Rearrangement of the original expression.
Okay, I mean, sure, but how would you go about it? How will rearrangement
Could you
happen?
like give me a minute? I want to just like arrange the angles and then like just figure out the angle.
I mean, I have no. Okay, sure. Yeah, sorry for rushing. But you got it. Okay, guys, so one tiny thing. Think trig. Okay, I mean, don't think inequality here. Please think trig. I mean, inequality works. Rearrangement works. I mean, I'm not sure how rearrangement works, and I'm not sure if it works at all. So,
No, not rearrangement inequality, just rearrange the expression.
oh, okay. Aha, you're going the right way. Yes, yes. Rearrange the expression, and you'll get something trigonometric. And honestly, this is a great problem. See. Uh,
I forgot, but what is the expression for like sine A into sine B?
um, 1 second. I don't remember. 1 second. I'll just find it out and tell you. 1 second. As far as I think, it's half cos A minus B minus cos A plus B. Oh my gosh, you were doing sine A times sine B. That is totally correct. Wow.
Wait, so cos A minus B minus?
Cos A plus B. You are going the correct direction. When you said sine A sine B, I totally understood that what you're talking about. But my advice would be don't go into breaking it down in terms of cos. Instead, like try to maximize sine A sine B. Any ideas, anything you can think of, please feel free to tell me. Even if you don't solve the entire problem, that's okay.
Just guessing, but is M the in-center maximally?
There. So, like, I was thinking,
Yes!
yeah.
Oh my gosh, you are the first person I saw who did this problem at the first chance. Wow. Had you seen this problem before?
No, but
Had you?
let me guess, it's IMOSL or along those
You
lines.
have seen it, man.
No,
Otherwise, how could you guess?
I've
Which
just
one?
seen like IMOSL usually has these expressions.
Oh,
Yes, it's ISL. Okay.
so
Wow.
I was trying to take, like, we have these 6 different variables, trying to convert them, trying to get less variables so that we can work with. So, like, if we draw the perpendiculars from M, then we can get some right triangles, which,
Yes.
like, taking angle ABC, MB, but you know, bifurcates into 2 angles. So
Mm-hmm.
the bottom one, so MBC,
Yes.
that angle, sine of it, so we could use the fact that we can express MA prime or dash, whatever, and MB using angle A, this
Yes.
angle MBC.
Okay. But yeah, but you guys are missing something important, and I wanted to highlight it. Okay, like try to think about this. Like if x plus y is a constant, then how to maximize sine x sine y
So X and
when
Y are MBC and MBA.
MBC exactly. Uh-huh. Okay. So I'll just answer this question like how to maximize
Yeah, so if you just like use the formula which we discussed, you can show the maximum.
yes. Or we could like okay, one more thing. Does everybody here know calculus like just normal differentiation of some basic functions? Guys.
Not exactly.
Uh, I don't know like sine and cos differentiation.
Okay. I mean we had like a calculus a Jensen class a few days ago, so I assumed that you guys would be familiar because
But we didn't do like sine or cos in the Jensen class, so
Yeah.
and not like we
that
don't
was in
have
the
Desmos.
prerequisites PDF, guys.
We have the Desmos anyway, so I'm like too lazy.
Okay. Okay, that works. But okay, so x is cos x and dx of cos x is minus sine x. Okay, that must be all.
Oh,
That
right.
is all.
Yeah, that is kind of like a common thing you hear other people say. Like like
Oh
that,
my
like other
gosh.
people keep on say that sine and cos are their own derivatives like that. That's
Oh
something
my
a lot of
gosh.
people say.
Okay. I see. I've never heard people say that, but sure, I guess. Okay, anyway, I'll just do this. So I'll just like do a little bit of it, not the entire. Okay. The sine x times sine y is basically sine x times sine c minus x, which is like I don't need to convert it to cos. That is the first thing. And one more thing, I think you guys know that like the maxima or minima is attained at like when f dashed x is 0. And we can find out if that is the maxima or the minima by calculating f double dashed x and looking at its sign. So is everybody familiar? Have you heard this?
Sorry, could you like repeat it?
Okay. So like the maxima or minima of a function is attained when f dashed x equals 0. So that is the first order derivative of that function. When
Yeah.
we equated to 0, the maxima or minima is attained. And how do we know that it is a maxima or minima? So for that, we calculate the double derivative. And if it is less than 0, then it is the maxima.
Okay, I haven't heard this. I haven't heard this
Okay,
yet.
like I think my method is easier than this. No way.
Okay, okay, tell me, please go on.
Yeah, like using the formula we discussed, you get
Okay, this one, right? Oh, okay, so we get half of, what do we get?
cos A minus B minus cos A plus B.
What is that in terms of x and
Okay,
c?
so that's sine, okay, C minus 2 whatever x in
Okay, I'll just write it down. Anyway,
minus
c
cos C,
minus
yeah.
2x
Minus
minus,
cos
it's
C.
not, yeah, minus cos c. Yeah, right.
Wait, cos C is constant. So to maximize it, cos C minus 2x should be maximized, which is found at 0 or 90, 0. Yeah, 0.
Okay, at c minus 2x equals 0. And I had c equals x plus y. So x equals y, that is where the. Or if I'm going to, I love calculus. So if I say this in derivative language, that f dash
So the
x
x
is
and
going
y
to
would
be,
give you the angle bisectors, and that's why the incenter is.
yes. So f dash x equals 0, so sine c minus 2x is 0. That is when, and this is also under the assumption that c is less than pi. So c equals 2x, and then we get the same thing. So, and it is going to be the maxima indeed, because f double dash x is going to be equal to, if I'm not wrong, going to be equal to minus 2 cos c minus 2x, which is less than 0. So yeah, so like the sine x,
Shouldn't the single
sine,
derivative be cos C minus 2x?
which one?
Wait.
This
Oh,
this
no,
one?
no, no, it's 0. Yeah, sorry, I made a mistake. It's sine.
It's fine. So sine x, sine y.
Cos.
Sorry, come again?
No, like it was the derivative of cos, that's why we get the sine.
Yeah, exactly. So sine x, sine y is maximum when x equals y. And therefore, like, coming back to our problem, I will mark these angles so it's easier to understand. This is alpha 1, alpha 2, beta 1, beta 2. I'm just marking them randomly, gamma 1, gamma 2. So basically what I have here, this expression like ma prime times mb prime times mc prime, this is equal to, what is a good color? This one, yeah. So this is equal to sine of alpha 1 times sine of beta 1 times sine gamma 1. Or this is also equal to sine of alpha 2 times sine of beta 2 times sine of gamma 2. So this was my motivation for maximizing sine of alpha 1 times sine of alpha. But basically, like maximizing this, yeah, so maximizing one of these seems arbitrary, right? Because we don't know how alpha 1 and alpha 2 are related. Are they equal? How much do they differ by? So we don't know any of that. So maximizing any one of them is not at all a good idea. So okay, so maximizing one of them is not at all a good idea. So we can just maximize the square root of their product. So like, their product is sine of alpha 1 times sine of alpha 2 times sine of beta 1 times, and blah, blah, blah.
Guessing again, is the maximal triangle the right angle triangle?
No,
No, right?
equilateral triangle.
Equilateral, huh? Okay.
Yes. So if I want to maximize this, we can just take the pairwise products like alpha 1, alpha 2, beta 1, beta 2, and we will be able to say that alpha 1 is alpha 2, beta 1 is beta 2, and gamma 1 is also gamma 2. Therefore, we have M is I gives maximum. Is that clear? We have solved the first part of the problem. Guys,
Yes.
okay. I mean, why is everybody so quiet? Okay, so we have another identity that is sine A by 2 times sine B by 2 times sine C by 2. I mean, since we have this is the incenter, we need to minimize this, right? I mean, maximize this, right? In order to maximize what has been asked.
Yeah.
So we have this theorem that it is like less than equal to 1 by 8 with equality when A equals B equals C. So the maximum is attained when all the three angles are equal and ABC is equilateral. Done. Is that clear, everyone?
So do you know the proof of it or you just stated it?
Yeah, I know the proof of it. It is by Euler's formula. I mean, I am overtime. I'm 15 minutes overtime, so I just didn't want to say this. Is it okay if I say it after the class time, like after the recording
Yeah, fine.
stops and all?
It's fine.
Yes. Okay. So thank you, everyone. I guess that's all I had to say. Yeah. Saidi, you can stop the recording, I guess.
Thanks a lot, Raya. Oh, it was really interesting.
You're welcome.
I can stop the recording now, right?
Uh-huh.